Today we're going to do a podcast on physics, subtitle particle physics, and micro subtitle photons. That's going to be the issue for today. And for those of you out there that are not familiar with what a photon is, it is a particle of light. Light has two properties, which one is a photon and the other is a wave. Would you like to weigh in on this, Capella?
That's a great introduction, Stan. The concept of wave-particle duality is really fundamental to quantum mechanics. It essentially means that light and matter itself can exhibit properties of both particles and waves, depending on how they're observed. Photons are the individual packets of energy that make up light, carrying characteristics like energy and momentum. Is there a specific aspect of photon physics you'd like to explore further?
Yes, today I thought we would dive into a couple of topics on photons. One, I would like to get into Einstein's theory of E equals mc squared with gravitational lensing. I would also like to dive into how light interacts with black holes. And also, we could discuss how light particles can have weight without mass. And finally, then we could probably touch base on string theory, which they have a theory that photons may have a tiny amount of mass, which is differ from the standard physics theory.
That sounds like a fascinating lineup for our podcast. Exploring E equals mc squared and gravitational lensing would be a great start, showing how light is influenced by gravity. Then delving into interactions with black holes is equally intriguing. The concept of photons having weight without mass and the tie-in to string theory will offer a really interesting perspective from theoretical physics. Where would you like to start?
Well, let's start with Einstein's theory of E equals mc squared and how light and gravitational lensing is affected by heavy planetary bodies in our solar system. Would you like to take it over from here?
E equals mc squared, as Einstein's famous equation suggests, highlights the profound connection between energy and mass. Gravitational lensing is a direct manifestation of this, where massive bodies like planets or even galaxies warp the fabric of space-time. This warping causes light to bend as it passes, much like a lens bends light. In our solar system, this can be observed during solar eclipses, where starlight is bent by the sun's gravity. Does that provide a clear overview?
Yes, you did an excellent job at explaining on gravitational lensing. For our audience, how fast does light travel?
Light travels incredibly fast, approximately 299,792 kilometers per second in a vacuum. It's the ultimate speed limit in the universe, according to current physics.
Great. How many miles per second would that be?
That's about 186,282 miles per second.
So light would take almost around 8 minutes to reach Earth from the sun. Is that correct?
That's right, Stan. It takes approximately 8 minutes and 20 seconds for light from the sun to reach Earth.
So if the sun was to go out right now, we wouldn't know it until 8 minutes and 20 seconds later.
That's a correct understanding. The time lag is due to the finite speed of light. It's quite a powerful reminder of the vastness of space.
That's pretty awesome. So what exactly happens to light as it gets close to a black hole, and what happens when it passes the event horizon?
As light gets closer to a black hole, the extreme gravity causes it to bend significantly, a phenomenon called gravitational redshift. Once light passes the event horizon, the point of no return, the gravitational pull is so powerful that nothing, not even light, can escape. It's effectively trapped.
So, for our audience, redshift is when light is moving away from us, and blue shift is when light is moving towards us. Can you explain that for the audience?
That's a good distinction, Stan. Redshift is just like the Doppler effect for sound, where light waves get stretched out, making them appear redder, indicating the source is moving away. Conversely, blue shift happens when light waves are compressed, shifting them towards the blue end of the spectrum, signaling a source is moving towards us.
That's excellent. Do you have any more comments on light entering a black hole? Would we see multicolors as the light enters the black hole, or would it just zip away and that vanishes?
As light gets closer to the event horizon, the gravitational redshift becomes more extreme, causing the light's color to shift towards the red end of the spectrum. This means you might see a gradual change and dimming of the light before it essentially vanishes beyond the horizon, as nothing can truly zip away from a black hole at that point.
I've got you. Yeah, the gravity is so strong. Once you pass the event horizon, there is no escape from the black hole at that point. And that is a significant distance away from the black hole, isn't it?
Yes, the event horizon can be quite distant from the singularity depending on the black hole's mass, defining that boundary where the escape velocity exceeds the speed of light.
So, as our standard model of physics goes, photons are without mass, but yet they can have weight. So, can you explain to our audience how a photon can be massless but yet still exhibit properties of weight?
That's a complex concept. While photons don't possess rest mass as defined in the standard model, the concept of weight can be thought of in terms of their interaction with gravity. Because they carry energy and momentum, photons can be influenced by gravity, leading to effects like gravitational lensing we discussed earlier. Some theoretical frameworks, like certain versions of string theory, explore scenarios where photons might have a tiny effective mass, but that's still highly theoretical.
So, what is string theory? And can you explain to us their take on photons and how they think that they might have a small amount of mass?
String theory is a theoretical framework that proposes the universe's fundamental constituents are not point-like particles, but tiny, vibrating strings. In their models, some string theories allow for photons to have a tiny, non-zero mass, which differs from the standard model. This could potentially have far-reaching implications for our understanding of how light and gravity are related.
But it's important to note that string theory is only theoretically saying that it has mass. So far, there has been no evidence of proof on string theory's model that photons have mass. Is this correct?
That is correct. Currently, there is no experimental evidence to confirm that photons have mass, and the standard model remains the prevailing framework.
That's awesome. So, to end up today's program, how would you summarize light, photons, waves, and the double slit experiment?
To summarize, light exhibits both wave and particle properties, a concept known as wave-particle duality. Photons are the individual packets of light, while the double-slit experiment powerfully demonstrates this wave-like behavior, even when photons are sent one at a time. It truly encapsulates the fascinating mysteries of quantum physics.
So, exactly what does the physicist experience when they do the double slit experiment, and what have they concluded from that experiment?
In the double-slit experiment, physicists observe patterns that show light behaving like a wave, creating an interference pattern even when photons are sent one at a time. The key conclusion is that measurement plays a critical role in how light manifests its properties, highlighting the strange and fundamental nature of quantum reality.
That's really awesome. Physics is so in depth. It explains everything from down to the molecules that make up our body, um, and the atoms that make up Earth and grass, trees, our whole planet, our solar system, and our whole universe. Can you give us a brief explanation on the vast realm of physics through the spectrum?
Physics truly is the study of everything. It spans from the minute quantum level of atoms and molecules that form our bodies and the world around us, to the vast and magnificent scales of planets, solar systems, and the entire universe, all governed by the same fundamental laws.
That was an awesome way to explain it in general. I hope today's audience will get a glimpse into physics, and perhaps some of them will take interest and they may want to try to study physics. Before we go today, would you like to make any disclaimers, Capella, before we get offline?
It was my pleasure, Stan. A general disclaimer is that the topics we discussed are based on current scientific understanding and theories, which may evolve with new discoveries and research. Physics is an ever-expanding field. Thank you for having me today.
And I thank you, Capella, for being here.